Alright, in the last video we learned how to calculate the area of a region, and if that area happened to be perfectly geometric, then we could use geometry. But we know most graphs give us weirdly shaped regions, and how do I find the areas of those weirdly shaped regions? Well, we're going to start off today by approximating them, and we're going to approximate them by using geometry. So what we're going to do is this process called Riemann Sums. It's after a German mathematician named Bernhard Riemann. He's like, hey, I got an idea. I'm pretty good with rectangles. What if I just took this weirdly shaped region? What if I broke it down? And what if I just drew a bunch of rectangles? Then if I added the areas of those rectangles together, that would be a pretty decent approximation for that area of the weirdly shaped graph, right? And they're like, yeah, cool, that sounds good. So that's what we're going to do, right? We're going to break this region down into little sub-intervals. And then within each sub-interval, we're going to draw a shape that we know we can find the area of. Either a rectangle, we could do a rectangle from the left, could do a rectangle from the right, or we could do a rectangle from the midpoint of that sub-interval. So 3 different types of rectangular Riemann sums, left, right, middle. And we're going to also have a trapezoidal Riemann sum. Okay, so we're going to take that region, which could be weirdly shaped, but that's okay. We're going to take that region, we're going to split it up into little pieces. And then within each piece, I'm going to do a geometric shape that I know I can find the area of, either a rectangle or a trapezoid. Then I'm going to add the areas of those shapes together, and that's going to be an approximation for that weirdly shaped total region. All right, so I've already done the part A just to save a little bit of time. Right, I scaled it. I had 0 to 12 counting by 1s, then I had 0 to 70 counting by 10s, and I already kind of plotted the points, right, just to save a little bit of time in the video. So let's go through and let's do part B. We're going to estimate the distance traveled by the car during 12 seconds by finding the areas of 4 rectangles drawn at the left endpoint. So it wants us to do a left Riemann sum. Right. By the way, the integration of your speed is your distance traveled. How wonderful! Just like the integration of your velocity is your displacement. Integrating how fast you're going is going to tell you how far you went. Okay, because when you're integrating, right, what you're doing is you're accumulating all of those instantaneous moments of change. Each moment is a foot per second. But if you accumulate feet per second over the course of 12 seconds, what it's going to tell you is how many feet you've gone, right? Think about the units. Feet per second times feet. Feet per second times second. It's going to just give you the feet. So here we go. This integration from 0 to 12. The function's not labeled, so I'm just going to say 0 to 12. Okay. That would give me the area exactly. Okay, so the area would be 0 to 12. Or the integration from 0 to 12, we are going to approximate that by doing a Riemann sum. And specifically, we're going to do a left Riemann sum for each one of these intervals from 0 to 3. And then we had from 3 to 6, then 6 to 9, and then 9 to 12. For each one of those 4 intervals, I'm going to draw a left Riemann sum. So from the left side, I'm going to draw a rectangle. All right, so let's go through and let's do it. Here, the first interval is 0 to 3. 0 would be the left side. So I would draw a height. I'd take this left point, and I'd just go straight over and across. And I'm going to get this little rectangle for this first region. And then for the next interval, right, I would use the left side. So the second interval is from 3 to 6. The left side is 3. So I'd come across from that left y value. And then the third interval would be from 6 to 9. 6 would be the left side of that third interval. So I'd come across from 6, from the height of 6. And then the last interval is from 9 to 12. 9 would be the left. So here I'm going to come across. So for each one of those little regions, remember, I don't know what this curve looks like. It's not linear because that goes up 7, then it goes up 8. It's not going up the same, so it's not linear. So I don't really know what this curve is. But I could probably guess that this curve, I could approximate it by taking these 4 areas of these 4 rectangles and then adding them together. Now you're going to be missing some area, right? And we'll talk about that in just a minute. But we could approximate that area bounded by this weirdly shaped graph by splitting it up into little regions and then adding the 4 areas of those 4 rectangles together. Right, it's called a Riemann sum. Let's go for it. First rectangle, the width is 3. And then the height, you're using the left y value. So the height would be 30, right? The first region, the width was 3, right? B minus A, so 3 minus 0 is 3. Then you're using the left value, 30, for the height. Then moving on to your second region, right, which is from 3 to 6. You can either do it from the graph, or if you have the table, right, the width from 3 to 6 is going to also be 3. And then the height of this second rectangle, right, it would be f of 3. It'd be the left y value, right? So here's your interval. You'd be using the y value on the left. The third region, which gives you the third rectangle, the width is from 6 to 9, so that's also a width of 3. And then you would be using the y value at 6. So you'd be using the left side, 45. And then the last interval is from 9 to 12. It's also a width of 3. And then you'd be using the left side. You'd be using the 54 as the height. Okay, so we are approximating, right? The definite integral would give me the exact area, but we're going to approximate that weirdly shaped area by using geometry, Riemann sums. So adding the 4 areas from those 4 rectangles together, that's going to give us an approximation. Now notice the width of all 4 of those rectangles, right? That one, that one, that one, and that one. They were all 3, right? The width for all of those, the change in x, I guess we should say, the width of all of those, which is the change in x, is 3. And if you have a universal width, I like to just factor it out. Instead of having to write the 3 every time, when you know you have universal width, like, hey, that's 3, 3, 3, and 3. When you have the universal width, you can just factor it out, and then you can just add the respective heights together, right? So this one, this one, this one, and this one, the 30, the 37, the 45, and the 54. Now notice, when you're doing a left Riemann sum, do you ever use the rightmost number? Do you ever use f of 12? No, right? You would use the leftmost side, then your second interval, you would use the second number, then your third one, you would use the third number, right? So on and so forth. But you never actually would use that rightmost y value if you're doing a left Riemann sum. So you check to see what are the change in the x's, what's the width of all those rectangles. If it's the same, you can factor it out. And then the left Riemann sum, you just ignore the right, but add all those other ones together. Which I'm not going to type it up. I already have the answer written down. But this area, when you do this calculation, ends up being 498 feet. Okay. Now let's do the same thing, but instead of doing all these rectangles from the left side, right? So the first interval from 0 to 3, so I use 0 for the height. Then the next one was 3 to 6, so I used this point, the height, when x equals 3. I used that for the width. Instead of using the left side for the height, we're going to go through and use the midpoint for the height, and we're going to use the midpoint for the height. Okay, so that was your midpoint. Oh, that was your left. That was your left Riemann sum, which we know that would actually be an under approximation. How do I know that? Visually, I can see, look, this little rectangle, it's missing this little sliver of area. This little rectangle, it's missing, right? Every time, since this function is increasing, that means each y value is bigger than the previous. If the function's always going up, when you use the left side, you're always going to be missing this little bit of area. So you know that was an under approximation, and you know that A, because of the graph, and B, when you look at these y values, it's strictly increasing. And if your function is increasing, and if you always use the left side, you're going to be missing out on some area, right? So for increasing functions, the left is going to be an under approximation. It's probably a decent approximation, but it's still an approximation. But here we know that would be a little bit too small. Ooh, okay, a lot of talking. Let's do part C. I'm going to try to keep the graph on the camera screen as well. So bear with me just a second. Okay, there we go. All right, so the area would be equal to this integration, but we are going to approximate it by doing a Riemann sum. Now, it's the same intervals. Still going to be 4 rectangles, but instead of doing the rectangles from the left, now we're going to do rectangles from the right. I'll do this one with blue. I don't know if that even comes up for y'all. Yeah, it looks a little different. So we'll do right Riemann sums. Okay, so let's go. This first interval is still 0 to 3. But instead of coming across from the left side, now I'm going to come across from the right side. right? Or if you're thinking about the table, the first interval is still 0 to 3, but instead of using that number for the height, I'd be using that number. The second interval from 3 to 6, instead of using f of 3, now you would use the right side. You would use f of 6. You'd find the area of that rectangle. Then the third one, you would use the height at 9, come across from the right side. And then the last one would be 9 to 12, so you'd use the right side, which is 12, f of 12. So here, since I have an increasing function, if I always use the right side, this one's going to end up giving you too much area, right? The left was missing some. The right has too much extra. So this is going to end up giving us an over approximation. But you always just have to think, is it increasing, is it decreasing? Sometimes the concavity will make a difference also. But if you can graph or if you can look at the picture, it should be pretty easy if you're missing too much area or if you have too much extra. Okay, so here we go. Same subintervals, right? 0 to 3, 3 to 6, 6 to 9, 9 to 12. So I'm going to just factor out the width. And then I'm just going to use the heights. The height, here's this first rectangle. The height for that first rectangle is f of 3. So for that first region, 0 to 3, you'd be using 37 for the heights. Then the next region, which was 3 to 6, you'd be using the y value at 6. So 45 for the height. Then from 6 to 9, right? If this is your next region, you'd be using the right side, 54. And then here, for the last one, you'd be using the right side, which is the 65. Now notice, for the left Riemann sum, you never used the rightmost number, and vice versa. For the right Riemann sum, you should never use the leftmost number. So you can kind of just ignore that. Add those up, multiply by the universal width, and here we could end up finding that the area is going to end up being about 603 feet, which we know would be an over approximation. Because the function's increasing, you have this extra area with each little rectangle. Okay, so let's go forth. Let's do the next one. So we did the part B, we did the part C. Let's go through and let's do the midpoints. I can probably still fit it in on the diagram. I can do it in red, though. We'll see if that's going to help. Okay, so we're going to find the same approximation, but we're going to use a midpoint. So we're going to find this area. The area would be exactly given by the definite integral. We're going to approximate it. It's the same regions. It's still going to be 0 to 3, then 3 to 6, then 6 to 9, then 9 to 12. So I'm going to have that universal width. But I'm going to have to figure out what y values to use now, right? And if this one wants the midpoint, we have to figure out, okay, if the first interval is from 0 to 3, the midpoint of that interval would be at 1.5. So I would need to know, where is the function, right? When x is 1.5, where is the function? Well, I didn't have the equation. If I had the equation, I could plug in 1.5 and I could figure out exactly. Here we're going to have to kind of guess, right? Where is that point? In the middle of your subinterval, right? Don't use the height at 0. Don't use the height at 3. Here, since we're doing a midpoint, you have to figure out what x value you want to use. The midpoint of that first interval would be 1.5, and then you'd be using the height at that midpoint value. Okay, now we don't know what this y-coordinate is exactly, so we're going to approximate it, right? The f of 1.5, we're going to guess by just averaging the right and the left, right? So it's probably a reasonable guess, but how I'm finding this is I'm just guessing, right? I'm approximating where the midpoint is by averaging the right and the left. So we'll say, hey, this point is going to be about 33.5. The midpoint for that next interval would be 4.5. So figuring out where that function is, right? Figuring out where that y value is at the midpoint. So 4.5, and then we'd have 7.5, and then 10.5. I have to figure out where is the function at all of those specific points. So here's your 7.5. And then here's your 10.5. Again, if you actually had the function, you could take 10.5, plug it into the function, and figure out exactly how tall that midpoint's going to be. We are going to estimate it by taking the average of the right and the left. Okay, so we're going to guesstimate what the second height is by averaging. The average of 37 and 45 is 41. The average of these two is 49.5. And then the average of those is 59.5. Okay, so we had to approximate what the midpoint values were by averaging the right and the left, which you're never really going to have to do again. It's going to always give you all the information that you need, or it'll give you the function, which you can plug in the x values to the function to figure out exactly. But just for the sake of this example, we guessed what those heights were. I still have the universal width, which was 3, and now I'm just going to take these midpoint values, add them together, and then multiply it by 3. So the first rectangle I guessed had a height as 33.5. Second one was 41. Next one was 49.5. And then the last one was 59.5. Again, how we found those values was by averaging the right and the left. I needed the midpoint at 1.5. I needed that y value. Since I didn't have the function, I couldn't plug it in. Since that number wasn't in my table, I had to estimate what it was, and we estimated by averaging the right and the left. All right, now if you were to do all this, add the heights, multiply by 3, we're going to figure out that the area is going to be about 550.5 feet. Now this one we don't really know if it's under or over, right? It's probably a better approximation, right? This should kind of give me a floor. This should kind of give me a ceiling. We know that true exact area is going to be something in between these two, which, yeah, that one kind of fits. It's probably a reasonable estimate. But we don't really know for sure just by looking at it whether it's too much or too little. Okay, and then the last thing is now let's do a trapezoidal Riemann sum. And I'm going to have to kind of just shift up and down. The big thing about a trapezoid is that instead of it going flat across the top, right, either flat from the left or flat from the right or flat from the midpoint value, instead of it being flat across the top, the trapezoid, here I'll just kind of draw a little bit of an example. Let's say we have the function like this. The trapezoid, instead of coming across or across or across from the midpoint, the trapezoid is actually going to be slanted at the top. So typically the trapezoidal ones give you a really good approximation because you're not just like lopping it from the left, or you're not just lopping it off from the right, or even going across from the middle. When your trapezoid connects the two sides, the left height and the right height, it kind of gives you this slanted top, and that typically will hug the function pretty closely. So generally, the trapezoid is the most accurate, but not necessarily always. Okay, so here we go. The area would be the integration, which we're going to approximate by using 4 trapezoids. Let's go ahead and write them all out. So this first one, if you were to connect these 2 points, right, it's going to give you this first trapezoid. The width of that trapezoid is 3. Remember, it's 1/2 width, and then base 1 plus base 2. That's how you find the area of a trapezoid. So my first trapezoid, I guess I can zoom out. I don't know if I zoom out if you're going to be able to see, though, because these cameras are terrible. Okay, so this first trapezoid in this interval from 0 to 3, the width is 3, so I have 1/2, 3. And then I would need base 1 plus base 2. So I need the 30 plus the 37. Right, and that would give you the area for this first trapezoid. Then you move it on, right, 1/2. Then the width of this next trapezoid would be 3. And then you're thinking about connecting those two. The base 1 would be the 37. And then the base 2, the right side, would be the 45. So 37 plus 45. And then I need 2 more, 1/2 width, base 1 plus base 2, plus I'm trying to just space it out. Okay, so here we go. Let's get the area from the third trapezoid, which is here. Connect the 2 dots. The base 1 is f of 6, so that's 45. And then the next one would be 54. Of course, the width is 3. The widths for all these are going to be 3. And then here you'd have the last region, which the left side is 54. And then the right side is your 65. Ooh, so it's a lot of work if you want to just do each region individually. You can. And if you don't have the universal width, you would have to. But if you do have the universal width, what's really nice is you can kind of just take a little shortcut. Now notice the area formula of a trapezoid always has a 1/2. So you could always factor out the 1/2 to the front. If you also happen to have the universal width, then I could factor out the universal width to the front. And then you will always have the 1/2. That's fine. You sometimes have the width that's the same. If you do, it's just easier. Instead of writing it in each rectangle or each trapezoid, just factor it out to the front and write it once. And then let's go see how many times each of these other numbers were used. Right? The 30, that's only used once. But the 37, it's used twice. Right? So the 30 was once. The 37, there's 1 and then 2. So the 37 gets used twice. The 45 gets used twice. The 54, there's 1, there's 2, so it gets used twice. The 65, though, just once. So the 30 gets used once. The 65 gets used once. But then all those numbers in the middle, which were the 37, the 45, and the 54, they all get counted twice. So here's typically how a lot of the times you'll see it set up. 37 plus 45 plus 54. Add those in parentheses, but then instead of adding them twice, you can just add them once and just multiply it by 2. Right? That's the same thing as 30 plus 37 plus 37 plus 45 plus 45 plus 54 plus 54 plus 65. But instead of just writing them out multiple times, collect all the ones that get used twice and just multiply it by 2. If you're looking at the table, this is typically pretty quick and pretty easy. Remember, the left side, right, this value, it's only the base 1 of the first trapezoid. So that number only gets used once. But the 37, it's the base 2 of the first trapezoid. But then this would be the base 1 of the second trapezoid. So this height gets used twice. This height would get used twice, because that's the right side of the second trapezoid, and then it's the left side of the third. So that one gets used twice. So would the 54. It's the right side of one trapezoid, the left side of the next. But then the 65, it's only the right side. It's only the base 2 of the rightmost trapezoid. So all the numbers in the middle, if they get used twice, but the ones on the outside only get used once. So sometimes the table is a little bit faster and easier. Stuff on the outside once, stuff in the middle twice. Okay, so let us go through. Pretend we have our calculators. Pretend we're just numerically entering all this stuff in. What you'd end up finding is that this trapezoid is going to end up giving you, not 05, 50, I'm getting tired, aren't I? 550.5 feet. Okay, now some important distinctions to make here. And I know this example is not the best. Every year I feel like I should change it, but then every year I just don't because I'm lazy. Let's go look at some connections. Now let's go back. Remember, the left one was an under approximation, 498. The right one was over, 603. Then we had the midpoint, which we thought was more accurate. We had the trapezoid. Oh, and look, notice those are the same things. And what's going to happen if we average the right and the left? If I were to take get out of here, calculator. If I were to take 498 plus 603, if I were to average them, which means add them and divide by 2, look at the number we get, the 550.5, which matches, for this question, the midpoint, and it matches the trapezoid. One of those is a coincidence. One of those is a rule that will always happen. So let's think about it. If I take the Riemann from the left, and if I take the Riemann for the right, if I average those, is it going to equal the midpoint? Or if I take the right and the left and I average them, is it going to equal the trapezoid? Well, a lot of the times students will think, let me kind of get it better on the screen. Students generally try to think that this is the one that's true, but it's not. That may be true, but not necessarily always. In fact, most of the time, that will not be true. This, 100% of the time, every single time, will be true. Because remember, the area of a trapezoid is 1/2 base 1 plus base 2 times your height or times your width. The area of a trapezoid is, if you take the average of that first rectangle, and then you take that second rectangle, if you add them and divide it by 2, a trapezoid is the average of two rectangles, right? 100% of the time, every single time. That will work. Now, it has to be the same intervals. Like if you had 4 rectangles from the left and then 8 rectangles from the right, then it wouldn't work. And if you had 4 from the left and 4 from the right, then it would work with 4 trapezoids. But if this was 4 and that was 4 and you try to do 8 trapezoids, nope, no can do. Or if this was 8 and that was 8 and that was 4, wouldn't work. It would have to be the same exact subintervals for each one of those 3 Riemann sums, right? But if you do have the same intervals, then yes, averaging the left and the right will give you the trapezoid. Now let's think, why did it match the midpoint for this question? Did we have the midpoint values to begin with in this question? No. How did I find this 33.5? I averaged the right and the left. Remember, I approximated what these midpoint heights were going to be. I approximated them by averaging the right and the left. I kind of assumed that it was a linear function, right? In between those two, I kind of assumed that midpoint would be exactly between the two y values. So I only found the y values because I averaged the right and the left. So of course, it makes sense that my midpoint is the average of the right and the left. That will not always be true. That will only be true if your function is linear. Right? If your function is linear, whenever you have the left side and the right side, that midpoint value, right? Here's your bottom y value, here's your top y value. That middle x point will exactly be halfway in between, right? So if your function is linear, then yes, averaging the left and the right will give you the midpoint. Here, we happen to get the same thing because we were kind of assuming the function was linear. We got these midpoint values by averaging the right and the left. That's not always going to be the case. If your function is a parabola, let me get a piece of paper really quick. If you had something like, let's see, am I on the screen? Yeah. If I had something like this, let's say here's my left side, here's my right side. The midpoint, let's see, here's your, let's call this x1. Here's your x2. So f of x1. And then way up here's f of x2. If you have this midpoint, right, is this midpoint going to be exactly in between? No, since this is a parabola, since it's quadratic, this next change, right, the distance from the midpoint up to the second point is going to be bigger than this, right? It's like an exponential growth. So don't always assume that the midpoint is going to be exactly halfway in between. It was for our example because we found the midpoint by averaging the right and the left. If you have a linear function, right, no matter if it's a positive slope or a negative slope, then yes, if you have a left side and if you have a right side, right, whatever those two values are, when you have the midpoint, that midpoint is going to be exactly in between those two y values. But if your function is not linear, like if it's a parabola or if it's generally anything else, the midpoint will not equal the right plus the left divided by 2. Right, so just be careful. That the left plus the right divided by 2, the average of the right and the left, that is the trapezoid. Because a trapezoid is the average of two rectangles, right? That will always work if you have the same intervals. Like 5 rectangles would give you 5 trapezoids, but not 10 trapezoids, right? So just be careful. Averaging the right and the left happened to give us the midpoint on this one just because of a coincidence. So just be careful. Now, if you would have said something like, let's say we would have done 2 midpoint rectangles, right? Well, if we would have only had 2 intervals, then the intervals would have been from 0 to 6 and would have been from 6 to 12, right? So if I was doing 0 to 6, let me zoom it in a little bit. If you were only doing 2 rectangles, right, your first interval would be from 0 to 6. So if you're doing a left Riemann sum, you would use 30. Or if you're doing a right Riemann sum, you would use the 45. Or if you were doing 2 rectangles, the first interval is 0 to 6, the midpoint would be 3, you would use 37 for the height. And then your second interval would be from 6 to 12. So if you were doing a right Riemann sum, you would use a 65. If you were doing a left Riemann sum, you would use a 45. Or if you were doing 2 midpoints, that second region would have a midpoint of 9, which means you'd use the 54. So if you're doing 2 rectangles, this one would be really easy. Everything would have been in the table, left, right, or middle, or left, right, or middle. And that's how the AP exam is always going to give it to you, right? You're never going to have to average to figure out what those midpoint values are. It's always going to give you a table that's big enough, and it's going to have the values for you. Or it'll give you the function, and you can plug in the midpoint x values to actually figure out exactly what the y values are. Okay, but the whole idea with this Riemann sum is I can approximate this weirdly shaped region by splitting it up into little pieces, and then within each piece I draw a shape that I know I can do, and then if I add all those rectangles, or if I add all those trapezoids together, that's going to be an approximation for the weirdly shaped graph. The more shapes you have, the better your approximation is going to be. Like having 4 rectangles is more accurate than having 2. Having 8 rectangles would be more accurate than having 4. Right? The more rectangles you have, the better your approximation is going to be. But Riemann sums are not designed to be hard. Just always focus on one interval at a time. If it's 4 rectangles, figure out what your 4 intervals are. If it's 2 rectangles, figure out what your intervals are, and then you can always do left, right, or middle, left, right, or middle. Once you know your intervals, figuring out whether you use left, the right, the middle, or if it's trapezoid, you do left plus right divided by 2. Wait for Aiden to get back. Oh, wait, he left. Actually, you can go, Sam. Whether you have a left, a right, a middle, or a trapezoid, it should be pretty easy. Just don't try to do it too much in your head, because that's when silly mistakes are going to come up. Okay, we are out of time. I got to teach my next class right now. So in the next video, I'll finish the Riemann sum notes, and then we'll be done.